तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
After having considered the various properties of Laplace transforms, we shall now take up applications of the Laplace transform technique to the solution of transients in networks and in systems in general. To start with, let us consider solution of transient problems in networks using the Laplace transformation method. In considering the network transients, we can first form the differential equation pertaining to the network and then transform the differential equation into the Laplace transform domain and arrive at the solution. This is a method that suggests by itself, and this is a more fundamental method. Later on we will discuss another technique which avoids some steps that we would have to go through in the differential equation approach. So let us start with the differential equation approach. The best way to do this is to go through an example. Let us consider a circuit in which there is a voltage excitation, there is a resistance, an inductance and a capacitance, a series circuit comprising R, L and C. Now we are interested in finding out the current in the circuit I. So the differential equation pertaining to the solution for the current given this forcing function E of t is given as the voltage drop across resistance is Ri plus L di dt, that is the voltage drop across the inductor, plus the voltage across the capacitor, that is Vc, that can be written as Q of t over C, that is the charge on the capacitor at time t divided by C, that is equal to E of t. This can further be written as, if you take the charge Q of t to be L di by dt plus, there is an initial charge in the capacitor, let us say Q0 divided by C, plus the additional charge that has been conveyed to the capacitor plates in the interval starting from 0 up to the point t. So that means 1 over C integral 0 to t I dt, that is equal to E of t. So what I have done here is, the Q of t has been thought of as comprising two parts. One is the initial charge on the capacitor, with this as positive and this as negative, and the additional charge that has been put at the capacitor plates in the interval 0 to t integral I dt divided by C. So Q0 plus the additional charge divided by C, that is the expression for Qt by C, is broken up into these two parts. Now in solving a second order differential equation of this type, it will turn out to be second order as we will see in a moment, we need to have no two initial conditions. So the initial conditions are associated with the reactive elements. So one is the inductance, the other is the capacitance. So the initial conditions we need to know to solve this problem are, first of all, something to do energy storage in the inductor to start with. So IL0 is to be found out, is to be known. And secondly, Vc0. This is Vc. IL0 is the same as I0 because after all the same current is flowing through the inductance also, Vc0. This is Q0 over C. So the knowledge of these two initial conditions are required in order to solve this differential equation. Now to find out the solution for this differential equation, what we do is we take the Laplace transform of each term on the left hand side and the term on the right hand side. So each one of these terms in the equation, their Laplace transforms are taken. So if the Laplace transform of I of t is capital Is, then Ri, when we take Ri, the Laplace transform of this would be, Ri is the Laplace transform of this R times I of S. The Laplace transform of this is L times di by dt. The Laplace transform of di by dt is SIS minus I0. Laplace transform of Q0 by C is a constant, therefore this is Q0 over Cs. And the Laplace transform of this 1 over C, integral 0 to t I dt has a Laplace transform Is over S. So this is 1 over Cs times Is. The Laplace transform of E of t, suppose is E of capital E of S, then this will be capital E of S. So term by term we do the Laplace transformation, and let us say the E of t has the Laplace transform E of S. Then term by term transformation of these terms will yield us R times I of S plus L times the Laplace transform of di by dt. Laplace transform of di by dt is S times I of S minus I0. S times I of S minus I0 plus Q0 over C, that is Q0 over Cs, that is Vc0 over S. Q0 over C is Vc0, Vc0 over S, plus 1 over Cs times Is, that is equal to the forcing function E of S. So we have an equation now in I of S which has to be solved for in terms of the known quantities. So I can write this as I of S equals E of S Laplace transform of the source function plus Li0 minus Vc0 over S divided by the coefficient of I of S on the left hand side, which is Ls plus R plus 1 over Cs. So what we have done is we have got an expression for the Laplace transform of the current in terms of the known quantities. E of t is presumably known, therefore E of S can be found out. The initial conditions in the inductor as regards the inductor current and the capacitor voltage are given, therefore these are found out. And L, R and C are parameters of the circuit, therefore we find I of S. And once we have I of S, IT can be found out as the inverse Laplace transform of I of S. This is the approach that we have to take up. Now a few comments on this. If you are interested in finding out the behavior of the current starting from t equals 0 minus onwards, then the initial currents in the inductor and the initial voltage across the capacitor, you can have 0 minus values. On the other hand, if you want the solution to be valid from t equals 0 plus onwards, then you can substitute 0 plus values and 0 plus values for both I0 and Vc0. So depending upon what type of solution you want, you can substitute either 0 minus initial conditions or 0 plus initial conditions. Let me put that down here. Comment. Depending on whether we wish to obtain solution from t equals 0 minus or from t equals 0 plus, we should substitute initial conditions pertaining to t equals 0 minus or t equals 0 plus. Remember, in the classical differential equation approach, we need to find out the conditions at t equals 0 plus in order to solve this differential equation. But here we don't have to do that. If you know the 0 minus conditions, and if 0 plus conditions are different from that, you need to substitute only 0 minus conditions, the complete solution is obtained. If 0 minus conditions and 0 plus conditions are one and the same, it doesn't matter whichever you substitute, it makes no difference. But if 0 minus and 0 plus conditions are going to be different, and you want the solution from 0 minus, you can substitute straight away 0 minus conditions. In the classical differential equation, we are perforce required to substitute the conditions as 0 plus. Sometimes if there is a transition from 0 minus to 0 plus, you have to make separate evaluation of the 0 plus conditions. That is avoided in the Laplace transform technique, as we can see here. Now the second point to observe is the differential equation is converted into an algebraic equation. You are not doing any calculus part here. All the derivatives and integral signs have been converted into equivalent multiplicative factors, and so a differential equation is converted into an algebraic equation. And we are trying to solve an algebraic equation really. So the steps that are involved here is first a differential equation. Connecting an output quantity y with an input quantity x. In general, we output quantity y with x. Then we convert this into an algebraic equation. Here the algebraic equation, the terms are the Laplace transforms of the output y of s, yt, and the input xt, so y of s and x of s. From the algebraic equation, you solve for the Laplace transform of the output quantity y of s. In this case, the current is the output quantity, so we have solved for I of s. So we solve for y of s. And once you have got that, you find the inverse Laplace transform and then get yt. So these are the four steps that are involved. You form the differential equation, convert this into an algebraic equation by Laplace transforming every term in the differential equation, then solve for the appropriate quantity which you are interested in. In this case, in our case, it is I of s. In general, it is a quantity y of s, and find out its inverse transform y of t. The fact that the initial conditions are substituted even at the stage of finding out the algebraic equation, in this process we are using the initial conditions, means that there is no separate requirement for the evaluation of initial conditions as we would have in the classical differential equation approach. The initial conditions are fed into the data at the beginning of the problem itself, and the evaluation of arbitrary constants, which is a troublesome feature in the differential equation approach, is completely avoided in the Laplace transform approach. So this is a way in which one can handle this. However, we would like to simplify this further. Since we are interested in finding out the electrical network transients, and this is a problem which occurs quite frequently, we would like to streamline these procedures and try to arrive at the formulation of the algebraic equation in this manner straight away without having to go through the intermediate differential equation. This is what leads to us what is called transform diagram approach. That is what we will take up later. Essentially what we will try to do there is try to write down this equation straight away without having to go through the preliminaries of setting up the differential equation and then trying to Laplace transform that. So this is the approach that we will take up, and that goes under the term transform diagram approach, and this is what we will take up next. The second approach we take for the analysis of network transients is what is called the method of using transform diagrams. Before we actually illustrate this method, let us look at some preliminaries. To start with, we will take the case of a capacitor. We know that the terminal equations of a capacitor can be put in the form that Vc of t is Q of t over C. So if you have a capacitor here, parameter C, this is Vc of t, and the charge on the capacitor suppose is Q of t, and the current is I of t, then at any point of time Vc of t is Q of t over C. We can write this Q of t over C as the initial charge on the capacitor at time 0 plus the extra charge that has been deposited on the capacitor plates in the interval from 0 to t. So 0 to t of I dt, that is the additional charge on the capacitor in the interval from 0 to t. This is the total charge Qt divided by C. Now this can be further broken as Q0 over C is the initial voltage across the capacitor, because that is the initial charge divided by the capacitor parameter C. Therefore, I can write this as Vc0 plus 1 over C integral 0 to t I dt. So in time domain, we have the capacitor voltage Vct as Vc0 plus 1 over C 0 to t I dt. This is the fundamental equation. Now, when we are analyzing a circuit in which a capacitor is situated, we should like to look at the relation between the currents and voltages in the transform domain. Therefore, we would like to express these quantities not in terms of time expressions but in terms of Laplace transformed variables. So what we would like to do is transform these quantities into their corresponding Laplace transforms. So Vc of t, suppose, has the Laplace transform Vc of s. Then that is the Laplace transform on the left hand side. On the right hand side, Vc0, that's a constant. Therefore, its Laplace transform will be Vc0 over s. Now, the second quantity, 1 over c times the integral I dt, this is a definite integral from 0 to t, which means if I of s is the Laplace transform of I, then 0 to t I dt has the Laplace integral 0 to t of I dt has the Laplace transform Is upon s, and of course we have c also, 1 over c also here. Therefore, I of s over cs. So this is the equation in terms of the Laplace transform of the terminal current and the Laplace transform of the terminal voltage. We have an additional term here, Vc of s and I of s are connected not only by the capacitor parameter, but also you have an additional term depending upon the initial voltage across the capacitor. Now this can be modeled by means of a circuit representation like this. Suppose I have a capacitor which, let us say for the moment, is an impedance 1 over Cs, and a current I of s is passing through it. Then if this is the generalized impedance, it develops a voltage here which is Is times 1 over Cs. So Vc of s is Is over 1 over C, Is over Cs, plus also you have an additional quantity which does not depend on the current. Therefore, this can be considered to be a source, a voltage source whose value is Vc0 over s. And this is the total terminal voltage across the capacitor. So we observe now that the terminals of the capacitor, suppose these are the two terminals A and B, in the transform diagram, in the domain, we can think of the capacitor to be represented by means of a circuit like this, where this capacitor has a generalized impedance 1 over Cs, in the sense the voltage across this capacitor in the transform domain divided by the current in the capacitor in the transform domain is 1 over Cs. So IFS passing through 1 over Cs develops a voltage Is over Cs. In addition, we have a voltage source Vc0 over S. Together will constitute the capacitor voltage in the transform diagram. We can express the capacitor, the current in the capacitor in terms of the voltage. So if we, from the same equation, you can write IFS equals Cs times VCFS, Cs times VCFS minus CVC0. So the current is now expressed in terms of the voltage like this. This can be represented by a similar diagram like this. You have a capacitor whose voltage is VCFS. Let me create a little more room here. I'll write this as IFS Cs times VCFS minus CVC0, which of course is also Q0. Therefore, I can represent this equation by means of a circuit like this, whose impedance is 1 over Cs, and in parallel with this, we have a current source whose value is Q0 in the transform domain. And the current here IFS, and the voltage across this is VCFS. So a voltage VCFS occurring across an impedance 1 over Cs will have a current here which is Cs times VCFS. So that Cs times VCFS minus Q0 is the total current, terminal current IFS. So this is a circuit representation of the capacitor in the transform domain. You observe that we are now modeling a capacitor in terms of a generalized impedance 1 over Cs, just as we have in this AC circuit analysis. You talk about the impedance of a capacitor as 1 over j omega c. In the transform domain, we are thinking of the impedance of the capacitor to being 1 over Cs. More about this later. Now, what is the corresponding situation for an inductor? But before that, let me make a small digression here to stress a particular point. Suppose I have a capacitor which is charged suppose I have a capacitor here. The initial charge on the capacitor, this is Vc of t. The initial charge of the capacitor, suppose, is gamma. I enclose this capacitor in a black box. Now let me take another situation where we have an uncharged capacitor in series with a voltage source equal to gamma, DC voltage source. So here this is Vc of t, and we have Vc of t is 0. In this case, Vct is 0. Vc0 is 0, that is initially uncharged. Vc0 is 0. So we have two situations. One, a capacitor which is charged initially to gamma volts, and another, a capacitor in series with a voltage source whose value is gamma, but the capacitor itself is initially uncharged. So if these two capacitors systems are given to you in two black boxes, they provide identical terminal relationships to whatever circuit to which they are connected. Or in other words, if you, from any external measurements, you will not be able to distinguish between these two. They have the identical terminal relations for all possible experimental situations. In other words, this is these two are equivalent for every possible conceivable excitation. And therefore, if you have a capacitor which is carrying an initial charge and therefore initial voltage gamma, we can represent this as an uncharged capacitor in series with a source. And if you take the Laplace transform of this, if this capacitor C has 1 over Cs as a dimension, as the generalized impedance, and a source which is gamma over S. So that's exactly the situation that we are having. Initial voltage across the capacitor can be represented as that of a source, and that source, a DC source, will have a transform like this. So these two tie up like this. Now, we can also think of an equivalent current source representation that will lead to this, but we will not do that. Now, let us look at the situation with reference to an inductor. We have an inductor L carrying a current I, and let us say the voltage across this is VL. We know that the current in an inductor, say I, equals the flux linkages in the inductor at any point of time divided by L. That is the defining parameter for an inductance. This psi of t, the flux linkages, can be written as the initial flux linkages plus the additional flux linkages that come up in the inductor as a result of an applied voltage, which is VL dt divided by L. After all, voltage is the rate of change of flux linkages, therefore flux linkages is related to voltage by an integral relation like this. This can be written as psi 0 over L, that is the initial value of the current in the inductor. So I0 plus 1 over L integral 0 to t VL dt. So that is the terminal relation of the inductor, the current in terms of the applied voltage, and the initial value of the current here that we have here. Now, we would like to represent this by means of a circuit diagram similar to what we had in the case of capacitors. Okay. So, taking Laplace transforms of these quantities, we have IFS, the Laplace transform of IT is IFS, I0 is a constant, therefore I can write this I0 over S, that is the transform of this. And again we have a definite integral from 0 to t of VL dt, therefore if VLT has a Laplace transform VL of S, this will be VL of S over S, and we have 1 over L also, therefore we have VL of S over S. That is the equation that describes the terminal relations of an inductor in the transform domain. Obviously, therefore, you have an equivalent circuit like this in the transform diagram which represents this equation. Suppose we say the inductor has generalized impedance L of S, Ls, and then the terminal voltage is VL of S. So the current in this portion is VL over Ls, but the terminal current is different from this by an additional current here, therefore you have a current source which is equal to I0 over S, and this is the terminal current IS. So the terminal current IS is related to VL of S in this manner. You have a parallel circuit, one contains the impedance, the inductor, whose generalized impedance is Ls, therefore VL of S divided by Ls is the current here. In addition, you have the source current here. Now, on the other hand, if you like to express VL of S in terms of IS, I can write this as VL of S equals, from the same equation, Ls times IFS minus L times I0, minus L times I0. So this equation lends itself to an interpretation in the transform diagram in this manner. So Ls is the generalized impedance, you have a current IFS, so that develops a voltage Ls times IFS. In addition, you have another voltage which is independent of IFS, therefore we can think of this as a current voltage source Li0 with this polarity. So the total voltage then is VL of S. So we have VL of S is IFS passing through Ls, generating a voltage Ls times IFS minus Li0. That's what we are having. Now, just as we have an inductor, a capacitor with a initially charged can be represented by an uncharged capacitor in series with a voltage source, we can also interpret an inductor carrying a current to be an uncharged a inductor which does not carry an initial current in parallel with a current source. So that is leave it as for you to work it out. And we can give the same interpretation in this case as well. Now, we therefore, for both the capacitor and the inductor, we have for each two equivalent representations, one in terms of voltage source and the other in terms of current source. Similarly here, in terms of voltage source, in terms of current source. We can use either of these equivalents for either of these situations, and depending upon the total circuit configuration, one or the other will be found to be more advantageous in many instances. For example, if you are using loop current basis, then you would like to reduce the number of loops, then a voltage source representation may be favorable. On the other hand, if you are using the node voltage method, a current source like this, so that the total number of nodes is still 2 here, whereas it will be 3. So a node voltage method may, in that situation, you may find the use of the current source more favorable. That, of course, depends upon the particular problem. Now, another comment here is that if you have A and B as the terminals of the inductor, here also these must be the terminals of the inductor, A, B. You should not think that these are the two terminals of the inductor. If these are the terminals of the inductor in the original circuit, in the transform diagram, you should not think these are the two terminals of the inductor. It is the entire branch, including the voltage source, which stands for the inductor in the transform diagram. Now, a few comments about what we have done so far. We see that unlike the AC circuit analysis, where we have impedances j omega L and 1 over j omega C, we have not only such generalized impedances, but also we have sources. If we did not have the sources representing the initial conditions, the inductance and inductor and capacitor are represented by impedances Ls and 1 over Cs respectively. So it is the initial sources which come into the picture. Initial conditions are the reactive elements which are equivalent to sources. On the other hand, we can say that if the capacitor has an initial charge and inductor has an initial current, they can be replaced by equivalent sources, and therefore here afterwards we can think of, in the circuit analysis problem, the effect of excitations or effect of sources on an otherwise unenergized circuit is what we are looking for. Because initial currents in an inductor and initial charges in a capacitor can be represented by equivalent sources, as we have seen. Therefore, without any loss of generality, we can think of a situation where we are considering the effect of sources on circuit elements which do not carry any initial current or initial charge, because those initial conditions can be replaced by equivalent sources. And once we have that, then the terminal voltage and the terminal current of inductors and capacitors in transform domain have a proportionality relationship. VC of S equals IS over CS, and VL of S is LS times I of S. So we have the concept of generalized impedances for both the inductor and capacitor. In the transform domain, the transform of the voltage has a proportionality relationship to the transform of the current, and so on and so forth. So these are called generalized impedances, and that's what we have to make note of. These generalized impedances are, after all, extensions of the impedances that we have in the AC circuit analysis. We know that in the AC circuits, 1 over j omega C is the impedance of a capacitor, j omega L is the impedance of an inductor. Here, instead of j omega, we have S. In the AC circuits, we are thinking of an excitation function which is e to power j omega t. It is on that basis we have derived the impedances in the AC circuit analysis. But here it turns out that we are thinking of excitation functions of the type e power st. Therefore, it is not surprising. Therefore, we land up on impedance functions generalized in a way as 1 over Cs and Ls respectively. So this is a generalization of the impedance that we use in the case of AC circuit analysis. A third point which we would like to make note of is, when you take the initial conditions, you are at liberty to choose either 0 plus conditions or 0 minus conditions. That is why in all this analysis I did not commit myself to saying whether it is 0 plus or 0 minus. You can use 0 plus or 0 minus. If you want to find out the system behavior starting from 0 minus onwards, then you have to use all the initial conditions pertaining to 0 minus. On the other hand, if you are satisfied with the determination of the network response starting from 0 plus onwards, you can substitute 0 plus conditions and carry out the analysis. So in all these conditions, I0, VC0 and so on can be either 0 plus or 0 minus consistently right through. After having said that, we know that in transient problems some switching takes place, let us say at t equals 0, and we are given, or at least we can find out, the conditions in the circuit before the switching operation takes place. That means 0 minus conditions are known to us in most of the situations. Therefore, it will be convenient for us to substitute 0 minus conditions, and the solution that we get will include the transition between 0 minus to 0 plus. We don't have to purchase additional trouble to find out the 0 plus conditions because they are not normally known to us beforehand, unless there is a continuity between 0 minus and 0 plus. So we don't have to take extra effort to calculate 0 plus conditions and substitute in these equations. It's enough if we take 0 minus conditions. And if there is any transition between 0 minus conditions and 0 plus conditions, that is automatically coming out in the final solution. And this is one of the advantages of the Laplace transform technique, as you will get to know when you work out circuit problems. We have considered the terminal relations of an inductor and capacitor in terms of the Laplace transformed variables. What about resistor? This is of course quite simple. If I have a resistor R carrying a current IT and the voltage across this is Vt, then straight away we know that V of t equals R times I of t at all points of time. Therefore, in terms of Laplace transforms, V of s equals R times I of s. So in the transform diagram as well, you have an R, this is V of s, and the current is I of s. So there is no difference between the transform diagram and the normal time domain representation of a resistor. The ratio of the time domain voltage to current is R, the ratio of the Laplace transform voltage to current is also R. So in general, if we have an element, a general element like this, and this is I of t and this is V of t, in the transform domain we have the Laplace transformed current indicated as the current variable and the Laplace transformed voltage as the voltage variable, and the ratio of the Laplace transform of voltage to the Laplace transform of the current, let us say with 0 initial conditions. That means we are assuming in the case of a capacitor and current, capacitor and inductor, there is no initial charge on the capacitor, there is no initial current in the inductor, 0 initial conditions. So Laplace transform of the voltage, the Laplace transform of the current, the 0 initial conditions. If these are Vs over Ifs respectively, this ratio will be equal to R for the case of a resistor. If this box contained a resistor R, that will be Vs over Is is R. If this box represents a pure inductor, this will be Ls. And if this box represents a capacitor, it will be 1 over Cs. So if this box, if this is X, R, if X is a resistance, if X is an inductor, and 1 over Cs if X is a capacitor. So we can think of this as a generalized impedance of this element, either R, Ls or 1 over Cs, and this of course can be extended to a combination of the elements. Suppose there is an inductor and resistance are in series, we can say the generalized impedance is R plus Ls, and so on and so forth. We can also think of this from the system point of view. Suppose I have represent this element as a system, and we have a current which is given by e to the power of st, and you want to know the output, the forced response of the system for these input conditions. This will be turn out to be, if the system happens to be a resistance, a current passing through a resistance, if this e to the power of st is the excitation to the system, and the forced response is equal to, after all, V equals Ri is the equation for a capacitor, for a resistance. V equals LdI dt is the equation for an inductor. V equals 1 over C integral I dt for a capacitor. Therefore, using these three fundamental relations, if the forcing function is e to the power of st, and the voltage will be R times e to the power of st. That is the forced response of the resistance. If the system happens to be a pure inductor, the relation between the voltage and current is L times di by dt, therefore this is Ls times e to the power of st. And if the system is a pure capacitor, the relation between the forced response of the voltage to the current, suppose treat this as a kind of differential equation, and I is the input e to the power of st, this is 1 over Cd operating on I of t. Therefore, if I of t is an exponential input, the forced response for the voltage is 1 over Cs times e to the power of st. So these generalized impedances R, Ls and 1 over Cs can also be thought of as a ratio of the forced responses of the voltage to the excitation, when the excitation, the current excitation, when the current excitation is in the form e to the power of st. So this is an alternate way of looking at this. So now that we have got this, we would like to set up the transform diagram of a whole circuit or a whole network in terms of these generalized impedances. To aid us in this process, let us recapitulate what we did in the case of AC circuits under sinusoidal excitation functions. We have a general circuit that is given to you. So instead of dealing with the I of t and V of t, sinusoidal voltages and currents, we represent in the circuit diagram the impedances of the various elements, j omega L, 1 over j omega C, or as the case may be. And instead of the raw currents and voltages in time domain, we represent them by means of phasors. So the whole entire circuit diagram can be written in terms of the variables being the phasors of the respective quantities, voltage and currents, and the element values, instead of being R, L and C, we write in terms of R j omega L, 1 over j omega C, the steady state impedance values. We do much the same thing in the transform diagram. What we do is we represent the circuit in the same form as we have in the time domain, except that we put down the generalized impedances of the various elements. And secondly, the variables that we are talking about are, instead of the time domain expressions, we will talk in terms of the Laplace transformed variables, the Laplace transforms of the various currents, the Laplace transforms of the various voltages. A third point which is new here is whenever the inductors carry initial currents and whenever the capacitor carry initial charges or initial voltages equivalently, then we represent those initial conditions by equivalent sources in the transform diagram. So we can have a voltage source representing the current in an inductor, initial current in an inductor, or a current source. Similarly, we can have a voltage source representing the capacitor voltage or a current source equivalently. So the only difference is that we have initial currents represented by additional sources, excitation sources. Otherwise, the diagram, the approach is very similar to what we do in the case of AC circuit analysis. We deal in terms of transformed variables instead of phasors. We deal with generalized impedances instead of sinusoidal steady state impedances. That is, wherever j omega occurs, we use S instead of j omega. That is the only difference. So this will be illustrated by means of an example which we will now take up to illustrate the technique of the Laplace transform to the transient analysis of a problem using the transform diagram. Let us take an example. We have a 10 volt source operating in a circuit comprising a resistance 3 ohms, 2 ohms, 1 Henry with a switch. This is 6 ohms and the switch is closed at t equals 0 after having been kept open for a long time. S is kept open for a long time and is closed at t equals 0. So we are asked to find out I of t for t greater than or equal to 0. Yes, so what we need to do is set up the transform diagram for this. So you have for the 10 volts, we straight away take the Laplace transform of this, so that becomes 10 over S, because after all it's a DC source, the transform of a constant 10 volts will be 10 upon S. The resistance 3 ohms is represented by 3 ohms again. This is 3 ohms, so you don't have to write ohms. The generalized impedance of the resistance is 3. Now this is 2. The resistance here is 2. As far as the inductor is concerned, its generalized impedance is S, because it's 1 Henry inductance, therefore Ls is S. But we must also have here Li0, a voltage representing the initial current in the inductor. And what is the initial current in the inductor? When the switch is kept open, 10 volts drives the current to the 3 plus 2, 5 ohms. Therefore, the current here IL0 minus is 10 divided by 3 plus 2, 5, 2 amperes. Therefore, Li0 is 2 volts, 2. So the strength of that voltage signal is L times I0, which is 2. We are substituting 0 minus values. In this case, 0 minus and 0 plus are one and the same, but we are substituting 0 minus values because they come naturally to us. And then you are having 6 ohms resistance. So we solve this equation in terms of the loop currents. After all, once we have the transform diagram, the equations are written down in exactly the same manner as we would do for DC circuits. So you write down the loop equations for these two loops in terms of the variables I1 of S and IFS. IFS is what we are interested in. So the first loop you have got total impedance is 3 plus 2 plus S, 5 plus S times IFS. The mutual impedance between loops 1 and 2 is 2 plus S, and the two currents are oppositely directed in this. So minus 2 plus S times, this is I1 of S, this is IFS, equals the total driving voltage in that first loop is in the direction of I1 is 10 plus S plus 2, 10 over S plus 2 rather. And as for the second equation is concerned, the total self loop impedance is 6 plus 2 plus S, 8 plus S times IFS, and the mutual impedance between loops 1 and 2 is S plus 2 as before, so minus 2 plus S times I1 of S. The total EMF in the second loop in the direction of I is minus 2, because this voltage tries to drive a current in the opposite direction, therefore this is minus 2. So you have two algebraic equations involving I1 and I. You can solve for IFS through elimination of I1 through determinants or whatever method you are having, and you arrive at the expression for IFS as 20 upon S plus 4 divided by 9 times S plus 4, and this can be written further as 4S plus 20 divided by 9S times S plus 4. So at this stage you make the partial fraction expansion for IFS in order to find IT. So if you carry out the partial fraction expansion, it becomes 4 upon 9 divided by S, 5 upon 9 rather, upon 9 over S plus minus 1 by 9 S plus 4. So in other words, I of t would be, once we have IFS, I of t would be 5 by 9 minus 1 by 9 e to the power of minus 4t. That is the expression for the current IT. So let us see what we have done. We started with this circuit diagram, replace this by a transform diagram, and from the transform diagram you set up the algebraic equations for pertaining to the transform diagram, and solve for the current IFS, the required variable, and find out the inverse Laplace transform. So the steps that are involved would be to set up the transform diagram, in the transform diagram you also with initial current sources, with initial condition sources, with initial conditions replaced by sources appropriately, either voltage source or current sources. From the transform diagram you set up algebraic equations, then get the Laplace transform of the response quantity whichever you are after, and then find the inverse Laplace transform response in time domain. For this you do the inverse Laplace transform. That then is the way in which we handle the network transient problems using the transform diagram. So we avoid writing down the differential equations pertaining to this. By once you have the transform diagram, the solution runs on very similar and parallel lines to DC circuit analysis. The equations are written in the same fashion, except instead of the DC quantities we write in terms of the functions of S, the currents and voltages are Laplace transform variables, and instead of pure resistances we write in terms of functions of generalized impedances. This is also very similar to what we do in steady state AC circuit analysis. Again, instead of phasors we use Laplace transforms here, and instead of impedances in terms of j omega we write generalized impedances in terms of S. As a matter of fact, the writing down the equations is simpler than in the case of AC circuit analysis, because we avoid complex numbers. Even though these are complex expressions, we are only using S. S is a complex variable, but the coefficients of all the values of S and their higher powers are real coefficients. Therefore, we don't see the complex numbers explicitly in writing down these equations. So this is the J terms which are strewn all over the place in the case of AC circuit analysis are avoided, or at least not seen here, and therefore it proceeds in a very smooth fashion. The major difficulty of course is the finding out the inverse Laplace transform of this. If IFS happens to be a complicated rational function, then the partial fraction expansion and finding out the inverse Laplace transform is that much more complicated. But however, the procedure is straightforward. So today in this lecture we have we took for consideration the application of Laplace transforms to network transient problems. We saw there are two different approaches. One is to start from the differential equation. This is a very basic approach, a general approach, and we should always keep this at the back of our mind because fundamentals are always very important. but then we would like to simplify the additional labor that is involved, because may have to do this type of problems again and again in order to simplify the work. Instead of writing down the Laplace transformed versions of the differential equation, which turn out to be algebraic equations, we try to find out a shortcut method of writing down the algebraic equations. That then we develop the theme of the transform diagrams, which is an alternative representation of the circuit diagram, and from the transform diagram we straight away write the algebraic equations, the equations of performance of the network, and from that we get an expression in Laplace transform of the response quantities, and we find out the inverse Laplace transform to find out the response quantity in time domain. That constitutes the solution of the tangent problem of a network. More about this in the next lecture.